Hello, my name is Amy Girling and I'll be speaking to you today about chemical bonding and states of matter. Today's training will focus on how the samples you work with bond together to form compounds and why they exist as solids, liquids and gases at room temperature. Understanding these principles will help you safely store, handle and utilise these substances effectively in your work. We'll begin by exploring the different types of chemical bonding. Chemical bonds form when atoms interact to achieve a stable electronic configuration. There are three main types of bonding: metallic, ionic and covalent. Metallic bonding occurs between metal atoms, ionic bonding occurs between metals and non-metals, and covalent bonding occurs between non-metal atoms. Electronegativity, or an atom's ability to attract electrons, determines the type of bonding. Metallic bonding occurs in metals. Atoms release some of their electrons, creating a sea of delocalized electrons. This allows electrons to move freely throughout the structure. These free-moving electrons allow metals to conduct electricity and heat, for example copper, which is used in electrical wiring due to its conductivity. Ionic bonding occurs when a metal donates electrons to a non-metal, which forms charged ions. Oppositely charged ions attract each other, which forms a strong electrostatic force. For example, sodium chloride is an essential compound used in food and medicine. Covalent bonding occurs when two non-metal atoms share electrons. The strength of this bond depends on the number of the shared electron pairs. Covalent bonding can be categorised into two types: simple covalent molecules and giant covalent structures. Simple covalent molecules, these consist of small groups of atoms held together by covalent bonds, such as water and oxygen. They generally have a low melting and boiling points due to their weak intermolecular forces. Giant covalent structures, these are vast networks of covalently bonded atoms such as diamond and silicon dioxide. These have very high melting points and are extremely hard due to their strong covalent bonds throughout the structure. For example, water has strong hydrogen bonds, making it essential for life and industrial applications, whilst diamond is used in cutting tools due to its hardness. The shape of molecules is determined by repulsions between electron pairs. Common molecular shapes are linear, which are have a straight line structure due to two bonding pairs. Trigonal planar, which have three bonding pairs spread out evenly. Tetrahedral, which have four bonding pairs forming a three-dimensional shape. And trigonal pyramidal, three bonding pairs and one lone pair, which pushes the shape slightly downwards. Trigonal pyramidal versus tetrahedral. Ammonia, NH3, has one lone pair, which repels the bonding pairs, which makes it pyramidal. The ammonium ion, NH4+, has no lone pairs, which results in a symmetric tetrahedral shape. CO3 2-, trigonal planar versus carbon dioxide, CO2, linear. Carbonate CO3 2- has three bonded oxygen atoms spreading out evenly in a trigonal planar shape. Carbon dioxide, CO2, has only two oxygen atoms bonded to carbon in a straight line formation, which makes it linear. Knowing whether a sample is a solid, liquid or gas at room temperature helps determine the storage requirements. Solids, for example sodium chloride, copper or diamond, are stored in dry, cool areas. Liquids, for example water and ethanol, are stored in sealed, labelled containers. Gases, for example oxygen, are stored in pressurised cylinders with safety precautions. The state of a substance at room temperature is influenced by intermolecular forces. Van der Waals forces, which are weak forces in noble gases and non-polar molecules, for example argon and oxygen, which are gases at room temperature. These forces are temporary attractions caused by the momentary shifts in electron distribution. There are dipole-dipole interactions, which are medium-strength forces found in polar molecules like hydrogen chloride gas, where permanent molecules attach each other more strongly than the van der Waals forces, for example hydrochloric acid, which is liquid at room temperature. There's hydrogen bonding, which are strong forces in water. They are found in molecules containing hydrogen bonded to nitrogen, oxygen or fluorine, for example H2O or NH3. This explains why water is a liquid at room temperature, while other similar sized molecules like methane are gases. Ionic bonds and covalent networks are the strongest forces leading to solids. Ionic bonds in compounds like NaCl, which is table salt. The strong electrostatic attraction between oppositely charged ions creates a solid lattice. Giant covalent structures are found in diamond and silicon dioxide, where the atoms are bonded in a vast 3D network requiring extreme temperatures to break the bonds. Thank you for listening to my presentation. If you have any questions, now would be the time to ask them.
I've got two questions. First question, why do metals conduct electricity but ionic compounds do not in solid form?
Metals have free-moving delocalized electrons that allow electricity to flow through. In contrast, ionic compounds have fixed ions in a solid lattice, and they only conduct electricity when dissolved in water or molten, because the ions become mobile.
Okay, and why is diamond extremely hard while graphite is soft if both are made of carbon?
Diamond has a giant covalent structure where each carbon atom forms 4 strong bonds in a 3D lattice, which makes it very hard. Graphite has layers of hexagonal rings with weak forces between them, allowing layers to slide over each other, which makes it very soft.
Okay.
Is that it for questions?
That's very interesting. Thank you very much.
Brilliant, thank you.